Hey guys, I'm starting a new motorcycle project. I want to electrify that Ninja 250. Let me preface this by saying that despite my technical background, prior to starting this project, I knew literally nothing about EV conversions. Also, while searching up EV conversions on YouTube and elsewhere, many of the tutorial type content seemed to emphasize the fabrication process, the assembly of the finished product, not so much on the technical details and how they picked those components and why they made the decisions that they did. With that in mind, as I'm making the video series for my project, I want to focus on the technical details and how I'm making the decisions for my project. So let's head back to the computer. I've put together some PowerPoint slides that will explain all the information that I've kind of curated so far and the decisions that I've made and kind of bring you up to speed with where I'm at right now.
Hey guys, so these first couple of slides are basically FAQs that I get asked all the time, and after we go over those, we'll jump straight into the system design and the technical details of how I picked the various components I'm about to talk about today. One of the very common questions is, why are you doing this? First off, I enjoy garage tinkering and project challenges. Also, I've been interested in electric vehicles for a long time. This is just the first opportunity I've had the time and the resources to actually try something. Separately, my wife has her motorcycle endorsement, but she never really had enough time in the saddle to develop the muscle memory to be confident and comfortable with, both hands, both feet operating the motorcycle. The clutch is a bit tricky, the shifter's non-intuitive for her, and if it was an electric vehicle where there's no clutch and there's no shifter, maybe this is what it takes to get her into motorcycling with me. Two other questions people ask all the time is, how much will it cost and what will the performance be, such as top speed and range? Turns out these questions are correlated. For example, if I bought more expensive components, I would have higher performance. My hope is that it costs $3,500 or less, and for target mechanical performance, I'm hoping to get to 70 miles per hour or freeway speeds. And I also want it to be able to travel 25 to 30 miles per charge. That should be more than enough for around town riding. Another question is, how will you do this? And step one is buy a donor motorcycle. That's the one you already saw in the garage. What's important about buying a donor motorcycle is it takes a lot of work out of it. I don't have to design a frame. I don't need to design a suspension. It significantly reduces the amount of welding required. The next thing I have to do is learn about electric vehicle motorcycle conversion. That is a work in progress, and hopefully I can use these videos to share what I'm learning along the way. Happening in parallel with number two is design a system that should work. And that's going to be what the majority of this slide deck is about. And last but not least is the fabrication and assembly steps. Realistically, that should be the easy part, but we can't really start that until we've got a good design that we can work towards. So speaking of design, this is an oversimplified representation of the major components that go into an electric vehicle. You got the electric motor that gives mechanical power to the wheel. You got your power source, the battery. You have a user input, so that's like your throttle. And the motor controller dictates how much of the battery power gets sent to the motor at any given moment. So with that in mind, this slide deck, I'm going to start by talking about my motor, or what criteria I use to select my motor, and then the motor controller, and then that user input, and then the battery. There's also a wide variety of miscellaneous additional items that we're going to just barely touch on today, but most of that's going to be in future videos. And then you'll see this cartoon several times throughout the video. Behind it, I've got this kind of stick figure diagram of a motorcycle. You can see the front wheel, back wheel, frame, forks, rear suspension. There's a kind of bulb there for where the gas tank is. And as I specify these components, I'll kind of lay out on here where those go. So, the motor. The first down select we need to do for the motor is pick whether I'm doing a hub drive or a mid drive. If you're not familiar, a hub drive basically replaces the rear wheel with a modified rear wheel, where the hub is replaced with a motor whose drive shaft goes all the way through, and when you hard mount the drive axle of the motor to your frame and you power the motor, the rim and wheel will spin. This ends up being very space efficient because the motor is not occupying space further forward in the motorcycle, but on the downside, it shifts the weight further aft, and also it becomes unsprung weight. If you're not familiar with that, unsprung weight is referring to weight that's not being supported by the suspension. So the wheels, they're just touching the ground directly. So if you hit a bump, that weight has to talk to the wheels directly, whereas the rider and the battery and other things that are going to be in the frame above the suspension, those are going to have a less jarring journey. By contrast, I could select a mid-drive motor. What's nice about a mid-drive motor is it's going to sit about in the same location that the internal combustion engine sits. Because it's sitting in that same location, the aesthetic of the motorcycle overall will look more like a traditional motorcycle. There's going to be a chain, a front sprocket, and a rear sprocket. Additionally, because it's on the frame, the weight distribution will remain similar and the suspension will be able to help carry it, and perhaps most importantly, the handling of the motorcycle will be more similar to the OEM design. Having considered those things, I'm deciding to go with a mid-drive motor. So once you've decided whether you're doing a hub drive or a mid-drive, you now need to decide whether you're going to use an alternating current motor or a direct current motor. Alternating current motors are more efficient but also more expensive. AC motors generally have much higher voltages. You'll see those more often in electric cars because they're bigger and heavier. Those work well with vehicles that have enormous batteries. From what I've read, electric motorcycles tend to almost always have direct current motors. If I down select from AC to DC, I now have to decide whether I want a brushed DC motor or a brushless DC motor. Biggest differences there is obviously the brushes, but also brushless motors are a little more efficient than brushed motors, and they're a little more expensive. Based on my research for my project, I think a DC brushless would be the best choice. So now I need to pick what size motor, and the size of a motor is not necessarily referring to the physical size, but there's a variety of performance metrics: the motor speed, the motor torque, the motor power. So I'm going to spend the next couple of slides telling you about how I decided those required characteristics. For motor speed, speed at which it rotates will dictate how fast your wheels are going. And I know that my target top speed is 70 miles per hour. If I can convert that 70 miles per hour into wheel rotations per minute and then multiply it by the gear ratio from the rear sprocket to the drive sprocket, I can then back out the motor speed. We're going to convert 70 miles per hour to linear speed. That means we need to know the circumference of the wheel. So if I go look at the tire of the Ninja 250, it says it's a 130/70-17. I didn't know what those numbers mean, so I looked them up for you. The 130 is the width of the rim in millimeters, and then the /70, that's referring to the aspect ratio. That's 70% height relative to width. And then 17 is the rim diameter in inches. Kind of weird that they're mixing units like that. Doesn't matter, that's convention. We're going to take the wheel diameter, 17 inches, and add 2 times this radius addition. So that's 0.7, that aspect ratio, times 130. And then we need to convert from millimeters to inches to match the rim. So divide by 25.4. So 17 plus 7.16 gives us 24.16 inches. So that's the diameter. And if we take 24.16 inches and just multiply by pi, then that gives us the circumference of the wheel, 75.9 inches. I actually put a tape measure on my tire and measured it all the way around. It was only 73 inches. Maybe it's a little worn, maybe it's underinflated, but for calculation's sake, I'm going to use 73. So the first thing we need to do is convert 70 miles per hour to inches per minute. Conversion there is 63,360 inches per mile, 60 minutes per hour. So I could take 70 miles per hour and multiply by the ratio of 1 hour to 60 minutes. So that means that I would be going 1.16667 miles per minute. And then again, I'll take 1.6667 miles per minute and multiply by the ratio of 63,360 inches per mile. Multiply it out, units work out to be 73,920 inches per minute. So now I've got inches per minute. I just need to convert that to rotations by dividing by 73 inches per rotation, and that works out to 1012.6 rotations per minute at the rear wheel. So if the rear wheel needs to be spinning a little over 1000 RPM, and the stock gear reduction between the drive sprocket and the rear sprocket is 3.071. That's the 43 teeth on the rear sprocket and 14 teeth on the front sprocket. If I multiply that across, the motor needs to be spinning 3109 RPM for me to hit 70 miles per hour. Anyways, going back to our motor sizing chart, we're going to put 3109 minimum motor speed. And that's assuming a stock gear ratio. Because we're using a mid-drive, I could get a custom rear sprocket and adjust that, in which case I would be trading low speed torque for top end speed or vice versa. Picking motor torque, I didn't really know how to calculate this, so I just looked up what the stock Ninja 250 motor torque is, and specs say that it puts out 22 Newton meters at the engine or at the drive sprocket, and if you take a Ninja 250 to a dyno and measure the torque output at the wheel, it's a little less, like 15 Newton meters, but because we're replacing the motor, I think it's more appropriate to use that 22 Newton meters as my benchmark. So I need to find a motor with at least 22 Newton meters of torque. And last but not least, here's the power equation. If you want to know more about where this equation came from, here's a YouTube link and a website. But basically, if I take that 3109 RPM and multiply it by 22 Newton meters and divide by 9.55, I get just a little over 8,000 watts of motor power required at top speed. I did a fair amount of Googling, I joined several Facebook groups, and I saw that a particular brand of motor is often used in these motorcycle e-conversions, and that's the QS lineup of motors sold by QS Motors. This particular one seems well suited to my application. It's the QS 13890H. Those numbers represent the physical size of the motor. It's 138 millimeters in axial length and 90 millimeters high, or diameter 90 millimeters. A couple of things to point out from the spec sheet here. The rated power for continuous use is 4,000 watts with a maximum power of 14,000 watts. At peak speed we needed 8,000 watts, so this should let us travel at 70 miles per hour, but only in short bursts, not necessarily sustained for long distances. The rated voltage for this motor is 72 volts. That'll be important for selecting other components. The max rotational speed is 7,000 RPMs. That's the unloaded speed. And so once you put some load on that, the max speed is going to be less than that. But remember, we only need like 3,100 RPM, so this is actually pretty good. The maximum torque output is 60 to 80 Newton meters. That's more than 3 times what I need. Should be pretty good. Waterproof grade here, IP54. That says it's resilient to splashing. I checked several other motors. That's a pretty common waterproof rating for electric motors for motorcycle e-conversions. So going back to our system design page, we've just now finished specifying the motor, and where that shows up on the bike is right here. We're going to mount it as low as possible in the frame and then have a chain connecting the drive sprocket to the sprocket on the rear wheel. So now let's talk about the motor controller. The motor controller should be compatible with the motor, obviously. In order to ensure that, you could hope that the vendor of the motor sells you the motor controller as a set, but more generically, you want the motor controller to have a higher power rating than the motor itself. That's because you don't want your components to limit or throttle your system capability. So the QS 13890H motor is rated for 4,000 watt continuous usage at 72 volts. So if I multiply that across using this power equation, E equals IV, I being the current, I need the motor controller to be able to handle 55 amps continuously. And separately, at peak operation, the motor power output is 14,000 watts. Divide that by 72 volts, I get 194 amps peak. So that means I need a motor controller that can do 200 amps. Lucky enough, the company that sold me the QS 13890H motor also sells a compatible motor controller, the Votol EM200. This is rated for operation of motors that are looking for 48 to 72 volts and it maxes out at 90 volts. That's actually helpful for the type of batteries we're going to use. We'll keep an eye on that. And then the peak current output here is 200 amps, which corresponds nicely with our motor peak current requirements. So this should work fine. So going back to our system design page, put a nice little green check mark next to motor controller, and if I look at my stick figure, I think I'm going to try and hide the motor controller in the fuel tank. So I'll just kind of cut out the underside of that and use that hollow space above that top frame element to hide the motor controller, and so that way it'll be out of the way of the battery and things. I think it'll fit in there nicely. Alright, so user input. Being that this is a motorcycle, the right form factor is a twist grip. If this were a go-kart or something, you could use a pedal, but basically I want the right side handle grip to be my throttle. Lucky enough, the QS Motor website that I got my motor from sells a kit that includes a twist grip throttle that's supposed to be compatible with the motor controller that I've already selected. You can see a picture of it right there, And nice things about it is it has all the specifications and performance criteria that matches my system so far. But also two nice things is right here is a little key interlock. That makes it so in order to ride this motorcycle you need a key. Without this it would be basically like a scooter at Walmart. You just hop on it and go. So that interlock is nice. And also the right side hand grip has this little display here, and that's supposed to show the voltage that is being commanded. Should be a really nice fit. So going back to our system design page, easy peasy check mark on the user input. If we show where that exists on our stick figure, it's going to be up here, right where the regular handlebars are. So now the hard part, the battery. So we know that we need 72 volts, and that was dictated by the motor. For the chemistry of the battery, there's a lot of options, but I kind of narrowed it down to either lithium ion or lithium iron phosphate. Lithium ion is really common, and maybe you've heard of like 18650 cells. This is the battery chemistry that's been dominant in the electric vehicle space for a while now, just because it's very energy dense. A little bit newer, but still a very mature battery technology is lithium iron phosphate. It's not quite as energy dense as lithium ion, but that means that it's less likely to catch on fire or explode, and it also works out to have more charge cycles of life, whereas a lithium ion battery might be able to get 1,000 or 2,000 charge cycles. Most lithium iron phosphate batteries are good for say 3,000 or 4,000 charge cycles. Based on my understanding of these two different chemistries, I'm going with lithium iron phosphate. So now I need to pick the number of cells to give me my 72 volts. Each individual cell is 3.2 volts, and I can just take 72 volts divided by 3.2 volts. That means I need about 22 and a half cells, but you can't buy a half cell, so that means at least 23 cells. But every single battery I've ever seen has an even number of cells, so we're gonna say I need 24 cells wired in series. And series is important because if you're combining batteries in series, the voltage adds up. Whereas if I was wiring these in parallel, then I would still only have 3.2 volts, but the capacity of the batteries would be added up. Many times while you're researching batteries, you'll see things like 24S, and that means 24 cells in series. Or you might see like 4P24S, where that P is cells in parallel, and then you could take multiple banks of parallel cells and put those in series. So we just mentioned battery capacity. Battery capacity is generally measured in amp hours on your typical batteries. It basically says how long the motor will be able to operate, which translates to the vehicle range. Let's dive down that just a little bit. I know my desired range is 25 to 30 miles per charge. If you're ever trying to figure out what the quote-unquote gas mileage of an electric vehicle is, that's generally measured in watt hours per mile. To figure out how many watt hours per mile I'm going to use, I would actually need my finished vehicle to measure how much I'm getting, because it depends a lot on the weight of the rider, friction in the system, air resistance. Looking at some various forums, they said that the rule of thumb for estimating for motorcycle power use is about 100 watt hours per mile. If you compare that to like cars, those would be 300, 400, 500 watt hours per mile, just because it's bigger, heavier vehicle, there's more friction, more wheels. Because we're a motorcycle, we've got a smaller cross section for aerodynamic forces and lower weight, fewer bearings. 100 watt hours per mile is a good estimate, but some motorcycle riders report up to about 150 watt hours per mile. So that's going to be my conservative assumption for my project. We're going to assume I need 150 watt hours per mile. If we're going to work out the math there, we say 25 miles equals whatever the battery capacity is in watt hours divided by 150 watt hours per mile. You multiply that across, you get 3,750 watt hours of battery capacity. But I mentioned a minute ago that battery capacity is generally expressed in terms of amp hour capacity. So we can use our favorite power law, P equals IV, to back out how many amp hours are in 3,750 watt hours. Take 3,750 divided by 72 volts, and that gives us 52 amp hours. That tells me my battery capacity should be about 52 amp hours, and that should give me 25 to 30 miles of range. That's approximate because we're never going to discharge the battery all the way, and in fact we're probably not even going to charge up the battery to 100% every time, just for helping maintain the health of the battery long term. So my actual amp hours available will be a little less than 52. but we were pretty conservative on our watt hours per mile, so I think with a 50 amp hour battery, we'll still be able to get 25 to 30 miles of range. So 50 amp hours of battery capacity. But now we have the problem of battery procurement, and the big decision here is whether I make the battery from cells or if I buy a pre-made battery. Making it is a little more complex because I need to literally wire it together and get my own battery management system, figure out my own charger. But that's perhaps an advantage rather than a disadvantage because it means I can make sure it's wired up robustly and I can get a high quality battery management system and I can get a high quality charging system. And also if I'm putting the cells together, I've got a lot more flexibility for the form factor. I can arrange it within the frame such that it's very space efficient. Whereas if I were to buy off the shelf some generic 50 amp hour lithium iron phosphate battery, it's gonna be pretty blocky and it's gonna have a built-in battery management system, probably the cheapest thing money can buy, and the charger is gonna be equally suspect. Based on that, I decided I'm going to make my battery from cells. And so now if I'm gonna buy cells, I need to decide whether I'm buying cylindrical cells or prismatic cells. There's also a third option, pouch cells. I didn't really look into those too much because I felt like I had enough options between cylindrical and prismatic. Cylindrical is a little less space efficient because packing cylinders together, there's air gaps between them. It also requires that you get a mini spot welder to put these cells in parallel so you can then add them in series, because an individual cylindrical cell is going to have a fairly small capacity. Whereas prismatic cells, you can buy them fairly large. You can buy a 50 amp hour individual prismatic cell and they're rectangles, so they stack together pretty nicely. So that being the case, I'm choosing a prismatic cell. So now I know I want a lithium iron phosphate battery that's 50 amp hours and I need 24 of these cells, and I'm going to get prismatic cells. But where am I going to buy them? They don't sell these at Walmart. So start Googling around for lithium iron phosphate suppliers. You find a bunch of really sketchy looking websites. AliExpress shows up all the time. Alibaba shows up all the time. And there's even a couple of Amazon links. Basically looking through all of these, seeing a lot of similar products, but the ones that are being shipped from China have really high shipping costs. And I made a whole spreadsheet. But basically, I ended up going with Amazon as my source of supply because I buy stuff from Amazon all the time. I've got kind of a higher level of confidence in their ability to deliver the product as advertised. If it doesn't work out, Amazon's there for returns, which I've had good success with in the past. So this is the battery that I found on Amazon. The title of the product is basically this long string of keywords, but it's literally exactly what I'm looking for. Lithium iron phosphate cells, 3.2 volts each. Individual cells are 54 amp hours. It's supposed to be a deep cycle battery so I can charge it all the way down and then all the way back up, maybe 5 to 95% of capacity. Another nice thing is it has screw connectors on the terminal, which means I don't need to weld anything. Down here, one of the most important metrics on here is 3C right here. That's something you'll see a lot when you're looking at batteries, and that refers to the current capable for charging and discharging. So you see maximum charging current is 1C, maximum discharge current is 3C. That number of C is a factor of the capacity. Basically this says I could charge these at 50 amps and I can discharge these at 150 amps. Now 150 amps is nearly triple the motor nominal demand and still 50 amps short of the max controller capability, so this should be fine. We're not going to burn anything out and we're going to get pretty close to our peak performance with these guys. At this point you might say, great, I'm all done with my batteries, but we're not, because these batteries need a battery management system. So the battery management system does a variety of things to manage the health of the battery long term. It will basically help prevent the batteries from overcharging while I'm charging them up, and it will also prevent them from over discharging while I'm operating the vehicle. Say my battery is dropping and dropping. When it hits 10% or 5%, whatever I've specified, the battery management system will say, all right, you're all done. There's no more power here. Even though there's still a couple percent left, preventing over discharge and preventing overcharge will be very helpful for maintaining the goodness of the battery over the long term. It also will balance the cells. So if one cell has an extra 0.1 or 0.2 volts more than other cells, so it's doing a little more work, or maybe it's doing a little less work, the battery management system will help keep all the cells at the same voltage level
which again is great for managing the health of the battery long term. It'll also prevent overcurrent. If there's too much current trying to be demanded from the batteries, this will prevent that from going, and again, battery health long term. If the batteries are getting hot, it can shut things down. Think of it kind of like a bouncer. Anybody that wants power to or from the battery, it's got to go through the battery management system, and that's what keeps the battery safe and healthy long term. And that's important because the battery is kind of expensive. While I was researching battery management system, 3 brand names came up over and over and over: the ANT, the DALI, and the JBD. I ended up going with DALI mostly because it's available on Amazon. And again, kind of like the battery cells, there's just a really long string of keywords in the title. It's got everything I need: 72 volts, 200 amps. It's designed for a battery that has 24 cells in series. It's got Bluetooth and an app, so I can specify where I want the cutoffs to be. And it's got what looks like pretty good documentation. So I ordered this, and I'm optimistic that this will do the job of keeping my battery healthy and safe over the long term. So now we're done with the battery, right? No, turns out we've got the battery specified, we've got the battery management system specified, but we need to charge up the battery somehow, and nothing we talked about yet provides energy to the battery. These are only things that are taking power from the battery, and so we need a charger. Peak healthy voltage per lithium iron phosphate cell is 3.65 volts, and so that means the charger must be able to provide 24 times 3.65 volts, or 87.6 volts. Before I realized that, I was Googling for a 72 volt charger and wasn't getting near as many hits as when I started Googling for an 87.6 volt charger. If I get a charger that's got some brains to it, it'll be able to optimize the charging time and battery life by transitioning from constant current charging to constant voltage charging during a given charge cycle. Maybe I'll try to mount it on the bike so I can charge it away from home with any old household AC socket, but we'll see how that goes. After Googling around, I found this one on Amazon. It again has a bunch of keywords. It seems like it fits what I need. It says it's designed for lithium iron phosphate. It's a smart charger for 24 cells in series for a 72 volt battery system. It says it's capable of 8 amps. So if you remember from the battery specs, the maximum charging current on these batteries is like 50 amps. So this is a safe amount of amperage to pump in. It's still 8 amps is no slouch. It's not going to charge in 20 minutes, but it's not going to take all day. It's got a lot of promising looking documentation with it. It shows the constant current transition to constant voltage. It says it does a lot of this battery protection stuff. So great. Ordered that on Amazon. So we finished specifying our battery management system, and our charger. And if we look at our stick figure motorcycle, I imagine the battery is going to take up most of the space in the middle of the frame. I imagine that the battery management system will be mounted on or near the battery somewhere, and if I'm lucky, the charger can fit under the fuel tank here. And I think it'd be fun to open up the gas cap and have the charger cord come right out of there. We'll see if I can get that to package in the space that I've got. So that's most of the system design. At this point, it would make sense to go look at our block diagram and see if we can't update it to include some of these other components that we've figured out need to be part of this. So here's our block diagram, and let's start by putting the names of the components that we know what they are. So my motor is a QS13890H, my controller is a Votol EM200, and my battery is a set of 24 lithium iron phosphate prismatic cells in series. Now, missing from here is the battery management system and the charger, so let's show that right now. The battery management system is going to be between the battery and the motor controller. So the motor controller can make a demand of the battery, and the battery management system can regulate that so it's not damaging the battery. And when it comes time to add power to the battery, we'll just send it through the battery management system. This chart is vaguely helpful, but not all of these arrows are equal. For example, the user input to the throttle will be low voltage, and therefore it can be a very thin wire, whereas the power going from the battery to the battery management system could be 150 amps, so those would be very thick wires. And the charging amperage, it maxes at 8 amps, so those would be thicker wires than those, but thinner than those. So let's color code these arrows to tell us a little more about what's going on. Mechanical power to the wheel, I'm showing in green. When we're spending electricity, those are yellow. Those would probably be the thickest wires. And we're storing electricity, that's coming from the charger to the battery. Those would be thick wires, but not quite as thick as the spending electricity wires. And then commands or data, that's going to be fairly thin wires. That's like the user input and commands from the motor controller to the battery management system. I was feeling pretty good about this chart, but as I was reading more about system design, I heard about a thing called a contactor. This is perhaps a great opportunity to leverage Cunningham's law. If you're not familiar, it says that the best way to find out the correct answer to something is post the wrong answer to the internet. Someone will correct you. So if you're watching this, please tell me if I've got this wrong. My understanding for a contactor is it needs to go between the battery management system and the motor. So there will be some sort of low voltage system that when I turn on the key on that throttle input, that'll physically connect the battery management system to the motor controller and allow voltage to pass through there. And when I turn off the system, it'll create a physical air gap between the battery management system and the motor controller. So the contactor will provide an extra layer of protection for the battery, but also it's a nice safety feature to prevent runaway discharge if there happens to be a short circuit from the battery. So that's everything, right? Nope, there's another thing. We need a DC-DC converter, and that's useful because there's a lot of bike systems like the headlights and the blinkers and the instrument cluster that all run on 12 volts, and I don't want to replace those with 72 volt capable components. So I need to be able to take 72 volts from the battery and siphon off a 12 volt stream there. To get that, I need this DC-DC converter, and then I need to distribute it to my 12 volt system. So this is what my general system diagram looks like so far, and in a future video I'll need to upgrade this to show actual wire gauges and which runs are positive, which runs are negative, and so forth. Anyways, this is about where I'm going to stop it for today. Work through the motor controller, the user input, the battery management system, charger. There's still a lot of miscellaneous stuff that we haven't talked about. For example, I want there to be a kickstand interlock so I can't ride the bike while the kickstand is down. Maybe I'll need to adapt the fairings to fit the battery underneath. There's a lot of stuff we haven't covered yet, but this allowed me to specify some of these big ticket items so I can order them and start laying them out and continue working on the project. Here's our final stick figure with a color code at the top there. I don't know, it seems like it might work. Hopefully it does. And hopefully this video is helpful to you. If you have any questions, please drop them in the comments. Maybe I won't know the answer, but I bet there's other people that will, and they could probably respond to you. If you want to follow my progress, make sure you subscribe. Thanks for watching. See you next time.